Okay, so we are going to talk about bounding geometrically integral del-Pezzo surfaces. So before I move on to the main content, I want to recall a couple of stuff. So first thing, recall that you call a family of projective varieties as bounded family. So you call chi, which is a class of projective varieties as a bounded family if there exist um, two finite type Z scheme Y and T, and there exists a flat projective morphism between them, such that these two are finite type Z schemes, such that whenever you pick up an element from this family, that means for all x inside curly x, where the global sections are given by these constants and constant in this field K, then there exists a map from spec K to T and an isomorphism, a K isomorphism from X to Y cross spec K. So if this thing holds for a class of projective varieties, then we call this family as a bounded family. In some way, we are trying to say that the parametrizing space for varieties in X is 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 of finite type, which brings the boundedness condition. Okay, so then the next thing I want to recall is this conjecture, VAB conjecture, which says the following thing. VAB conjecture. VAB conjecture says that for any rational number, epsilon strictly greater than 0, the class of Fano varieties of dimension D and which have x's which have EKLT singularities, this forms a bounded family. So this BAB conjecture was actually first given by, actually there is, so people, so B stands for Borisov. Both the B's is like both Borisov brothers, and A is Alexeyev. So it was, I think, around the same time when Alexeyev proved this thing for dimension 2 in characteristic 0, and Borisov brothers showed it for toric varieties. So that there is no fight. So there's Borisov, Alexeyev, Borisov conjecture it's called BAB conjecture. Well, let me just recall what EKLT singularity are roughly. So we remember that if these KLT singularity and these kind of singularity are defined for a pair and not for just the variety. So you consider a pair and then recall how we define KLT. We would consider a log resolution from W to X, and then we look at its this thing canonical equation, which looks something of this sort. Kx plus b, and then we say that X is going to have a KLT singularity if there exists a log resolution such that the coefficient of this thing, we say that XB has KLT singularity if the coefficient of BW are strictly less than 1. You say that it is KLT if the coefficients are strictly less than 1 minus epsilon. You must note that this epsilon is strictly greater than 0. Okay, I mean in the BAB conjecture. So BAB conjecture in general is not true for E equals 0, that is for KLT singularities. Okay, just a note to take. And the examples, counterexamples exist in quasi-elliptic surfaces. Okay, only in surface case only, um, E equals 0 does not hold for conjecture. Okay, so let me say what has been known already about this conjecture and what is open. Okay, so Alexeyev solved this problem um, for characteristic 0, dimension 2. Then, like I said, Borisov brothers did it for toric varieties. Second, McKernan and Zhu did it for some um, particular cases which require some technical terminology, and I'm skip that here. But all this is happening in characteristic 0, and finally Professor Birker solved this fully for characteristic 0, right? So in characteristic P, it is open. Then its generalization for Calabi-Yau is also open and is worth thinking. Then, before I move on to what the paper has, a little bit of motivation on why BAB conjecture is important. Well, it's good to have boundedness condition on the parameterizing space, but there is like a real... So Prokhorov and Shramov, these two people were studying birational automorphism group through birational rules. And then they realize that if you have BAB conjecture, then you have this Jordan property for rationally connected varieties. I do not have an expertise over there, but I just felt like it's good to have something linked with, like, it makes the reading of BAB conjecture more important. So now what this paper by Bernasconi and Martin say around BAB conjecture is the following. So they say that the following classes of del-Pezzo surfaces. So del-Pezzo is like the Fano surfaces. Del-Pezzo surfaces are bounded over spec C. And these classes are following. So first class is of del-Pezzo surfaces, which are geometrically canonical, geometrically integral canonical, del-Pezzo surfaces. So they form a bounded family. Then there are two more classes. Another one is del-Pezzo surfaces, which are geometrically integral and tame. Tame is a kind of singularity where what you require, I'll actually introduce as I come to that. So the second class that they say is bounded is X, which is geometrically integral, and tame, it's EKLT, and it's del-Pezzo. And then finally, the third class is all the EKLT del-Pezzo surface such that the characteristic of the global section field or global section ring will be equal to 2, 3, 5. And I must remind you, we are interested in the case where 2, 3, it's like if it is equal to 235, then we are interested in finding a counterexample in there. But for that, I felt like maybe we should understand what goes in the proof, because it doesn't take a long period of time, to be honest. So maybe in this talk, I'm going to completely describe, or let's say I'm going to describe the complete idea of what makes the first class at least bounded. And we can talk about other things later, maybe, if we require. Like we can just walk as much as, like we can change the directions as we move forward. Okay, so let me talk about the proof of why, if I take del-Pezzo surfaces, which are geometrically integral and canonical. So I'm taking all the x which are geometrically integral, canonical, and yeah, that's it. Del-Pezzo surfaces. Why do they form a bounded family? Okay, so I think the goal of this entire talk is going to be to describe why this form a bounded family. Okay. Okay, but before that, let me recall what these terminologies are, for the sake of completeness. So this word geometrical always means that when you take take base change to algebraic closure, the property remains. So you will say that x is geometrically integral if you take its base change to algebraic closure, and it still remains integral. So if this is integral, then you say it is geometrically integral. And actually, this term and this word geometrically, you can put in front of anything. You can put this geometrical word in front of canonical. And what it will mean is that you are taking x to be canonical. And then when you are base changing it to algebraic closure, then x, this thing is, it remains to be it remains to have canonical singularities. And similarly, geometrically normal. So you pick up a normal, base change to algebraic closure, and if it still remains normal, then your x was geometrically normal. And then so on. Geometrically normal, you can define geometrically integral, geometrically reduced, geometrically canonical, phalana dhimkana. So this geometrically is gonna be repeated. This terminology is going to be repeated again and again. Canonical singularity is in line with KLT singularity. I think I defined it somewhere. Yeah. So I defined this KLT singularity over here. So all these singularities that are defined in minimal model program are like they all are dependent, or let's say they all are defined using the coefficients of this BW. Okay, so canonical are the one where you require the coefficient of BW to be less than equal to 0. Okay, so then those are canonical singularities. So I think over the time when people are trying to show something or use the information that it is canonical, they are not really interested in these coefficients. What they're more interested in is, so canonical singularities are the singularities where MMP hold, and I think KLT are the one which is like the smallest class where vanishing theorems hold. So I think over the time people not be interested in कि उसका coefficient क्या था. I think they'll be more interested in कि अगर KLT है तो MMP काम करेगा या vanishing theorem काम करेगा. So anyways, so, and then del-Pezzo is just the Fano condition on surfaces. Okay, so let me start with the first thing that I have over here, which is geometrically integral. Okay, so okay. Okay, so geometrically integral means it is when you are taking algebraic closure, it still remains integral. Now, Tanaka in his paper has talked about 4 invariants, which are hard to mention all of them, but let's say some of them are like this. So what do these invariants do is, it's a little bit of digression that I'm talking right now. So these 4 invariants, they determine how much far a thing is from being geometrically integral, geometrically reduced, or geometrically normal. Like each of these invariant is going to have a different property. Let's say, for example, this ex over k is called thickening exponent, and what it measures is, so if your x is geometrically reduced, then your e of x over k has to be equal to 0. Okay. And if it is positive, then definitely your x is not geometrically, I mean, this implies it's not geometrically reduced. So basically, what happens is that, so you will see in the definition the way we'll define this thickening exponent. So this kind of geometrically normal, non-normal, or geometrically integral, these kind of phenomena occurs more in imperfect setup. If your field extension is separable, it usually base change, after base change it still remains normal. It's not big that big of a deal. So what happens is this thickening exponent is going to measure the smallest amount, like small, it measures the small, this how close you require the inseparable extension so that it start to become geometrically normal or geometrically reduced. I mean, whichever one we are talking about. But let me say more maths than English. So one of the invariants that I'm going to talk about amongst these four invariants that are talked in Tanaka's paper is this thickening exponent. And how it is defined is, so what happens is, if you take x, right, and then you base change it to k over 1 over p to the infinity, and then if you consider its generic point, and then you consider its local ring, the local ring at the generic point of this ring, let me call this as r, okay? Then the length of r over r turns out to be a power of p, okay? And this power, we are calling it as thickening exponent, okay? So what happens is that if you take geometrically reduced thing, then your thickening exponent turns out to be 0. Okay, this is also there in this paper, and then these invariants are discussed more briefly in this paper. If you want, you can look at it. But the only information that I want to extract from there is that, so right now what I'm trying to show is that my this class is bounded, right? And all I have all the varieties that I have are geometrically integral. So in general, they're also geometrically reduced. So what I have is that for our varieties, e of x over k is equal to 0. Now you might wonder, why did I bring this invariant into the picture? So if I have to tell you the sketch of how somebody would show something is bounded is the following. Okay. I mean, it's going to be displayed in the proof also as I move forward, but let me summarize it a little bit over here. So what's going to happen is we are going to show two things. Okay. First is we are going to show that the canonical divisor self-intersection of the canonical divisor is actually bounded by some number. Okay, this should not be displayed right now, but it will be bounded by some number. Okay, and then we will also show that some power of so we know that minus kx is ample because we are dealing with del-Pezzo surfaces. But if we can find out what power of it is going to be, so we know ample की कोई ना कोई power very ample होती है, right? But if we can figure out what power is going to be very ample, then we can talk about the Euler characteristic of so let's say this. So what I'm going to do is my omega inverse is going to be ample, and I'm going to show that omega x minus 12 is very ample. This is going to give me an embedding of x inside some Pn. Okay, and this Pn is also going to be bounded by capital N. Okay, now the Euler characteristic of this guy will be bounded. Reason being, Riemann-Roch is going to give me that the Euler characteristic is well, Euler characteristic is just a number. What I wanted to say is that if you look at the Euler characteristic, Riemann-Roch gives you that it's going to be something of the form 1 over 2 and then minus 12 kx and then something like that. Then you can define Hilbert polynomial using Euler characteristic. I think maybe I should write more things than just saying. But the sketch is the following. You will first bound kx square by some number. That's going to give you that the number of Hilbert polynomial corresponding to your omega x minus 12, which is giving you an embedding of x inside some Pn, is bounded, as in there are only finitely many Hilbert polynomials. And then Grothendieck tells you that corresponding to each Hilbert polynomial, you have the parameterizing space is like a finite type variety, right? So all this coming together is going to give you this finiteness condition, or let's say the boundedness property on the class of, on your class of projective varieties. So basically the key idea inside this whole proof is bounding the self-intersection of kx square and then having a suitable power of omega inverse to produce an embedding of x inside Pn. This will be bounded by minus 16 and 12 is less than 16. All these things are going to play role together. So let me just continue. I think I said a lot of things in the air. Maybe I should write things more. So coming back to why did I introduce this invariant is because the idea of these invariants is interlinked with, so what E of x, what is in the thickening, what is the value of this thing thickening invariant is interlinked with the self intersection of kx, and how are they linked is what I'm going to tell. So for now, what I have is that I have geometrically integral. So I pick a simple, I pick an element inside this class, and I know it's going to be geometrically integral, and then the thickening exponent of this thing is going to be 0, and there's going to be two. There can be two cases. It is geometrically integral, but it's not necessarily geometrically normal. And it's in general not true that if you have something geometrically integral, then it turns out to be geometrically normal. So what we'll do is we'll distribute this into two cases. One is geometrically normal and the other is geometrically non-normal. Okay, so either my x is going to be geometrically normal or it's going to be geometrically non-normal. Okay, so what happens is that in general, if you consider a geometry, so this is the first thing that you have. You also have that it is canonical, it has canonical singularities, right? So we're going to use that also somehow. So in general, if you have geometrically canonical, then that implies geometrically normal. And why is that true is because when you consider the definition of canonical singularities, over there you're basically considering a pair, and in this pair one requirement is that x has to be normal. Okay, so it's by definition only, whenever something is geometrically canonical, it has to be geometrically normal. It is embedded inside the definition only. But the opposite in general is not true. But there is this something nice thing about canonical del-Pezzo surfaces, that the opposite also holds. So if you take canonical del-Pezzo surface, and if it is geometrically normal, then it turns out to be geometrically canonical, which is great, right? Now you might want to ask what makes canonical del-Pezzo surfaces so special that this thing holds. So there are two things. First is, if you take so on Gorenstein, sorry, spelling is going to be wrong, but because it's maybe I'm going to put it on YouTube. So sorry. So on a Gorenstein normal surface, canonical singularities are same as rational singularities. Okay. And then you have classification of del-Pezzo surfaces. Classification of del-Pezzo surfaces. These two things together are like the two main pillars of showing that geometrically normal implies geometrically canonical. Okay, so this phenomena doesn't hold in general because you don't have classification of any, like you don't have this kind of classification thing which happens in like del-Pezzo surfaces. Okay, so in the case where you have your x to be geometrically normal, in that case you have that it is geometrically canonical. Okay, so it's a geometrically canonical del-Pezzo surface. So what you want to do is you want to take the algebraic closure. You want to take the base change to algebraic closure, and it still remains canonically del-Pezzo surface. And now there is this classification that canonical del-Pezzo surfaces are either, so this is definitely true for non-singular del-Pezzo surfaces, which is in even in characteristic P, that it's either isomorphic to P1 cross P1 or it's isomorphic to P2 blown up at D many points where D is less than equal to 9 or less than equal to 8. I mean, I'm not sure if you can blow it up on 9 points. And in which case, the degree, which is like the kx square, we define this as degree of the del-Pezzo surface. This is equal to the number of points you blow up. Okay. For the case of P1 cross P1, I think D is equal to 8 or it's equal to 1. It's either 9 minus 1 or it's 1. In any case, what we would like to conclude from this case is kx square is going to be less than equal to 9 when you have geometrically normal. Okay. So like I said, what we want to do is we want to bound the self-intersection of kx, and that's going to give us nice things. So for now, what we have done is we have picked up geometrically integral surfaces. We have divided them into two cases. One is where it is geometrically normal, another is where it is geometrically non-normal. If it is geometrically normal, because it's already canonical, it becomes geometrically canonical, and that gives you some classification where you have that it's going to be blow up or P1 cross P1, and that gives you some information about what kx square is going to be. It's going to be bounded above by 9. Okay, so keeping geometrically normal aside, let's say our x is not geometrically non-normal, in which case the Bernasconi and Tanaka has told us that this non-normal case doesn't always hold. I mean, this holds, but it only holds for finitely many prime. And those primes are p equals 2 and p equals 3. So if your p is strictly greater than 5, then geometrically non-normal case is not going to happen. Like this kind of not nice things is not going to happen. It's always going to be geometrically normal. Okay, so the hindrance primes are only 2 and 3, and we have a way to deal with it. And that is where that thickening exponent is going to come into picture. So in the same paper, what they show is that if p is equal to 2 or 3, then kx square is bounded by 12 times 3 e of x over k when p is equal to 3, and it is 6 times 2 e x over k. Okay, when p is equal to 2. So because your e of x over k is equal to 0, what you get in this case is that kx square is going to be less than equal to 16. Okay, so that is why I introduced the thickening exponent, because it has some relation with bounding kx square. So your kx square, all in all, combined both cases, is always going to be bounded above by 16. Okay. So keeping that information together, let's move forward. So I'm going to claim here that omega to the minus 12 is very ample. in both the case. I'm going to proceed with assuming the claim and then I'm going to prove the claim if time allows, or maybe next time. So let's say we know that omega x to the minus 12 is very ample. Okay, then what do we do is that it's going to give me an embedding inside Pn. Okay, and then as this n is also bounded, omega x minus 12 is going to give me a um, um, an embedding. Okay, and then recall that if you have an embedding of by minus kx of x inside some Pn, then you can define an Hilbert polynomial corresponding to it by Pn equals chi of x f of n, like corresponding to any line bundle f. You can define an Hilbert polynomial, and then I'm trying to define line bundle for minus kx, and I think I'm defining it for minus 12kx. So you define this Hilbert polynomial corresponding to it. Okay. Now, Grothendieck tells you that corresponding to any Hilbert polynomial, there exists a Hilbert scheme over spec K, right? And a closed subscheme X, which kind of give you the same parameterizing condition as you want when you were defining a bounded family. So basically, Hilbert scheme parameterizes a scheme of PM with a fixed Hilbert polynomial. So if you have a fixed Hilbert polynomial, then there is a Hilbert scheme which is compact, which is for finite type, which parameterizes your space. So if a class of variety has only finitely many Hilbert polynomial, then the projective models lie in only finitely many such Hilbert scheme. Okay. Now kx square being less than equal to 16 tells you that the possibilities of Hilbert polynomial is just finitely many. Of Hilbert polynomial corresponding to chi x omega x minus 12 is finitely many. Okay. Why? Because Riemann-Roch gives you that chi of omega xd is equal to half of d minus kx plus chi of ox, right? And then you plug in d equals minus m kx. Okay, that's going to give you chi of omega x minus m kx is equal to half of m plus 1 times kx square plus chi of omega x. So if you are able to bound this and kx square, right? So what happens is that we will show, I mean, this is also there in this paper, that we show that this omega x so is always 0. Actually, h0 is always 0. And then you can also say about h1 and h2. And then you can bound this. So all in all, like this is true for a more general variety, but then kx square is bounded is going to give you that there are only finitely many possibilities for Hilbert polynomial, and it's going to give you finitely many Hilbert schemes, which will collect all the elements in your class of projective varieties that you were considering, and then that gives you like the boundedness condition on the family. Yeah, so we still need to prove the scheme, prove the claim that omega x of minus 12 is very ample. So the proof of this thing is a little technical. They're going to use one lemma where they're going to show that if you have del-Pezzo surface, like they're going to divide, again, they're going to divide this into two cases where your x is geometrically normal and in another case it's non-normal. When it is non-normal, then you have only finitely many primes to deal with because Tanaka and Bernasconi tells you that this non-normality doesn't hold for large enough primes, which is after p equals 5. So for the normal case, you will have for the normal case, For the normal case, you will get that omega x minus 6 is very ample. And I forgot the proof right now. And in the non-normal case, you will have um, you will have to use one lemma which says something like this. It says that if you have geometrically reducible variety of dimension n, and A is any line bundle which is globally generated ample, and L is any ample line bundle which is zero regular with respect to A, then A tensor L is very ample. Okay. And then what happens is that when your P is equal to 2 and 3, then you can say something about O of minus 3 L, where L is is a general hyperplane. So what I'm trying to say is the proof of this thing is a little technical. We can discuss this next time, because I did not dwell much into this because I was more interested in knowing what is the idea of the proof. So the main idea, if I have to sum up, is the following: that if you bound the kx square, then you're able to say something about how many number of Hilbert polynomial are going to be there, provided you have some information about chi of Ox. And once you have that, if you have only finitely many Hilbert polynomial, then your family is bounded. Then there's no problem. So this was the main issue. Like, and why Fano are expected to behave nicely is because they're going to give you some kind of embedding inside some PN, and then you can talk about this Hilbert polynomial and all these things. And I think this is the only way how you bound these moduli spaces, or you say a family is bounded. So I'm gonna end the talk right now, but this is all I wanted to say. I hope you have a good day.